Hey there, science fans! Today we're diving into the fascinating world of pressure with Pascal's principle. This principle helps us understand how fluids behave under pressure, and who better to guide us than the brilliant mind behind it all? Blaise Pascal! Blaise Pascal was a French mathematician and physicist who lived in the 17th century. He was a true Renaissance man, making groundbreaking contributions to mathematics, physics, and even philosophy. But today, we're focusing on his work with fluids and the principle that bears his name. Get ready to unlock the secrets of pressure. Before we jump into Pascal's principle, let's talk about pressure. What exactly is it? Pressure is the force applied over a certain area. Think of it like this. If you press your finger against a wall, you're applying force. The smaller the area of your fingertip, the greater the pressure you exert. In fluids, pressure works a bit differently. Imagine a balloon filled with air. The air molecules inside are constantly bouncing around, colliding with the balloon's walls. These collisions create outward pressure. We can calculate pressure using a simple formula. Pressure P equals force F divided by area A, or P equals F divided by A. Easy peasy. Now let's see what happens when we apply Pascal's principle to this pressure. Pascal's principle states that a change in pressure at any point in a confined fluid is transmitted equally in all directions throughout the fluid. This fundamental concept in fluid mechanics is named after Blaise Pascal, a French mathematician, physicist, and inventor. He discovered that pressure applied to a confined fluid is distributed evenly, which has profound implications in various fields, from engineering to everyday life. Sounds complicated? Let's break it down with a simple example: a balloon. Balloons are not just for parties. They can help us understand complex scientific principles in a fun and visual way. Imagine squeezing one end of a balloon. The pressure at the point where you squeeze increases. You can feel the tension in the rubber as it stretches, and you might notice the balloon bulging out in other areas. According to Pascal's principle, this increased pressure is transmitted equally throughout the entire balloon. This means that the force you apply is not just localized to the area you're squeezing, but is spread out evenly across the entire surface of the balloon. That's why the balloon expands in all directions, not just where you're squeezing it. Pretty cool, right? This principle is not only fascinating, but also incredibly useful in designing hydraulic systems, which rely on the even distribution of pressure to function effectively. Another way to visualize Pascal's principle is with communicating vessels. These are a set of containers that are connected at the bottom and filled with a fluid, often used in laboratory demonstrations to show how pressure works in a fluid system. These are containers connected at the bottom and filled with a fluid. When you pour liquid into one container, it doesn't just stay there. It moves through the connection to the other containers. No matter the shape or size of the containers, the fluid level will always be the same in each one. This is because the pressure at the bottom of each container must be equal, ensuring that the fluid distributes itself evenly. This happens because the pressure at the bottom of each container must be equal. If one container had a higher pressure, the fluid would flow from the high pressure area to the low pressure area until equilibrium is reached. If the pressure were higher in one container, the fluid would flow into the other until the pressures were balanced. Pascal's principle in action. This principle is crucial in understanding how various fluid systems work, from simple water tanks to complex hydraulic machinery. It shows us that even the most complex systems can be understood through simple, everyday examples. Pascal's principle isn't just theoretical, it's the driving force behind many everyday machines. This fundamental concept in fluid mechanics states that pressure applied to a confined fluid is transmitted equally in all directions. This principle is the backbone of numerous hydraulic systems that we encounter in our daily lives. One of the most common applications is in hydraulic systems. These systems are designed to use the incompressibility of fluids to transmit force efficiently and effectively. These systems use fluids to transmit force and do work. By applying pressure to a fluid in a confined space, the force can be multiplied and directed to perform various tasks. Let's look at some examples. Hydraulic presses. These machines are a staple in manufacturing and metalworking industries. These powerful machines use Pascal's principle to generate enormous force. They can crush, shape, and mold materials with precision and power that would be impossible with manual labor alone. A small force applied to a small piston creates pressure that is transmitted to a much larger piston. This allows the larger piston to exert a much greater force, making tasks like metal forming and material compression much more efficient. This larger piston can then lift heavy objects. Hydraulic cranes. These cranes are essential in construction and shipping industries. Similar to hydraulic presses, hydraulic cranes use Pascal's principle to lift and move heavy loads. They can handle weights that would be impossible for traditional mechanical systems. The operator controls the flow of fluid to the hydraulic cylinders, which extend or retract to move the crane's arm. This precise control allows for the safe and efficient movement of materials on construction sites and in industrial settings. Car brakes. When you step on your car's brake pedal, you're actually activating a hydraulic system. This system is crucial for the safety and performance of your vehicle. The pressure from your foot is transmitted through brake fluid to the brake pads, which then clamp down on the rotors to slow or stop the car. This process happens almost instantaneously, providing the quick and reliable stopping power that modern vehicles require. These are just a few examples of how Pascal's principle is used in everyday technology. The versatility and efficiency of hydraulic systems make them indispensable in many fields. From construction equipment to airplanes, this principle is essential for countless machines we rely on. In aviation, hydraulic systems control everything from landing gear to flight control surfaces, ensuring the safety and functionality of aircraft. In industrial machinery, hydraulics power everything from assembly lines to robotic arms, making modern manufacturing possible. Section 5, a bottle, some tubes, and Pascal's power. Today we're diving into the fascinating world of fluid mechanics and exploring Pascal's principle. Want to see Pascal's principle in action? It's a fundamental concept in physics that explains how pressure is transmitted through a fluid. You can easily demonstrate it at home with a simple experiment. This is a fun and educational activity that you can do with your family or friends. You'll need a plastic bottle, water, and a few other items that you might already have at home. 2 syringes of different sizes are essential for this experiment. The different sizes will help us see the principle in action more clearly. And don't forget the tubing that fits snugly onto the syringe nozzles. This will help us connect the syringes and allow the pressure to be transmitted. Here's what to do. First, fill the bottle partially with water. Make sure not to overfill it, as we need some space for the syringes. Next, connect the 2 syringes with the tubing. Ensure the connection is tight to prevent any leaks. Then fill 1 syringe with water. This will be our source of pressure. Leave the other syringe empty. This will help us observe the effect of the pressure transmission. Insert the ends of both syringes into the bottle, making sure the ends are submerged in the water. This is crucial for the experiment to work. Now push down on the plunger of the filled syringe. Apply a steady and firm pressure. Observe what happens to the plunger of the empty syringe. You'll notice that it moves outward. This movement occurs because the pressure you applied to the first syringe was transmitted through the water and tubing to the second syringe. This is a perfect demonstration of Pascal's principle, which states that pressure applied to a confined fluid is transmitted undiminished in all directions. This principle is used in various applications, from hydraulic lifts to braking systems in cars. So next time you see a hydraulic system in action, remember this simple experiment and how it illustrates the power of Pascal's principle. Section 6. Building the world with Pascal construction and beyond. Pascal's principle isn't limited to simple machines. It plays a crucial role in many industries, including construction, manufacturing, and even medicine. In construction, heavy machinery like excavators and bulldozers rely on hydraulic systems that operate based on Pascal's principle. These systems provide the immense power needed to move earth and lift heavy materials. In manufacturing, Pascal's principle is essential for processes like injection molding and metal stamping. Hydraulic presses used in these processes shape and mold materials with incredible precision. Even the medical field benefits from Pascal's principle. For instance, some medical devices use hydraulic systems for precise movements during surgery. Prosthetics also utilize hydraulics for smooth and controlled motion. Section 7. Not always so simple, limits to Pascal's principle. While incredibly useful, Pascal's principle isn't without its limitations. It's essential to remember that this principle applies primarily to confined, incompressible fluids like liquids. Gases, being compressible, behave differently. When pressure is applied to a gas, its volume can change significantly. This compressibility means that the pressure transmission throughout a gas might not be perfectly equal in all directions. Temperature also plays a role. Fluids, like most substances, expand when heated. This expansion can affect the pressure within a confined system, leading to deviations from Pascal's principle. Section 8. Pascal's legacy: pressure's lasting impact. Pascal's principle, though simple in its concept, has had a profound impact on our understanding of fluids and their behavior. From everyday objects like car brakes to complex machinery used in industries worldwide, this principle is a cornerstone of modern technology. As we continue to explore the world around us, Pascal's legacy reminds us that even the simplest scientific principles can have far-reaching consequences. So, the next time you squeeze a tube of toothpaste or marvel at a hydraulic crane lifting tons of weight, remember the genius of Blaise Pascal and his remarkable principle.